All right, so I actually don't have a solution for Ruby Warrior, but I have been thinking about it a little bit and came across some interesting techniques that I thought I'd talk about, and might be useful potentially to solve the intermediate level. But at this point, I've just barely scratched the surface with this technique, and came about because I've been coming to these meetings for the last few months and working on this problem, and I did come up with a solution to the beginner level at least, but even that was basically just spaghetti. It was really ugly brute force solution. And then I think James or Doug or somebody talked about using the command pattern as a solution, and I thought that was a lot nicer than what I had come up with, but there were still some limitations in that things had to be ordered correctly from the outset, and you couldn't really adjust to a dynamic situation in the same way. So I actually started going back to my old AI textbook from college and was looking at all kinds of stuff and kind of went down a rat hole. And the solution I ended up looking at actually came from an outside source from the game development community. So there's this concept called behavior trees. And behavior trees are kind of like a combination of a finite state machine. And if you're familiar with AI, there's a setup called heuristic task network planning. So it's a way of breaking down tasks into subtasks and providing heuristics for making decisions. And so a behavior tree is kind of like a combination of those two things. So I thought I'd try it out with Ruby Warrior. It actually went pretty well. This is not my presentation here. I just stole this from an article about behavior trees on aigamedev.com, I think. So this technique is kind of becoming popular in the game development world. So academics might not follow this approach, but practicing game programmers probably do. So the idea of a behavior tree is that it allows you to build up behaviors in terms of groups of atomic actions or conditions. So you build up this tree, and the leaves of the tree, these white guys here, they're one of two things. They're either a condition, which will just return true or false, or an action, which will actually have some effect on your world. So in this case, the actions will be like Ruby Warrior actions that James showed, the attack or the walk or whatever the case may be. And the branches of the tree can be one of a number of things. One of them is a sequence. So a sequence is kind of like an AND operator. It means evaluate all your child nodes, and the result of that evaluation is all those things like a logical AND together. And as soon as one of your child nodes returns false, you bail out of that and just cut out of that subtree entirely. Kind of similar is the selector. This is basically a logical OR. It evaluates all the children of that branch, and if any of them return true, then the whole subnode or the sub-branch returns true. So the first one to return true in a selector is going to cause that branch to terminate and percolate up. There are others they talk about, such as parallel selectors and sequences that do things concurrently, but that wasn't really needed for Ruby Warrior, so I didn't really get to that. And
that's because in Ruby Warrior you can only do like one action a turn, right?
Yeah, and that actually has an impact on the way you have to design your tree. So I'll talk about that. But yeah, so if we go back to this diagram here, you see that I mentioned that all those white nodes there, the leaves, are either a condition or an action. And like James mentioned in the Ruby Warrior problem, you can only call one action per invocation of that play turn method. So if you just naively evaluate this whole tree, you're going to end up calling multiple actions in a given turn. And Ruby Warrior is going to throw an exception when you do that. So you have to kind of program around that. So, but anyway, I thought this was a potentially interesting approach. Started out just trying to do like a finite state machine, and the state transitions got a little messy, so that's when I started working with this approach. And I looked around for a existing Ruby solution for behavior trees, and there was one on rubygems.org, but I guess it's dead, and the GitHub project has been deleted. So, and it doesn't even work if you try to download it. So I basically end up having to build this behavior tree implementation from scratch. But I'll show some of the details if you're interested in that. But kind of just wanted to show how I applied it to the Ruby Warrior problem. So let me blow this up some. All right, so this is my stateful warrior class. This is I think James did a similar thing with his implementation. I think yours was mindful warrior. Yeah, so it's a warrior that remembers things. The only difference that I had with mine is I used this delegator concept instead of explicitly using method missing to propagate things. So the idea here is that Ruby Warrior passes in a new warrior instance every time it calls this play turn method, but you kind of want to remember things in your warrior and not get a new instance each time. And so we both had the idea of just capturing state in a stateful kind of warrior class, and I used Ruby's built-in delegator concept to accomplish that. So if this class here, or if this object doesn't respond to a given method, it's just going to pass it on to its delegate. So if I call something that this doesn't respond to, it's going to end up going to the underlying warrior implementation. So just kind of saves you the trouble of having to implement method missing to forward along that invocation there. But other than that, this is basically just a warrior object, and the behavior tree stuff comes in this define behavior tree method here. So, oops. So we'll take a look at that. So I mentioned that behavior tree has leaf nodes that are either conditions or actions, and it has branch nodes that are selectors or sequences. And I kind of created this little DSL that is not very good at this point, but it gets the job done to kind of build up this tree from those atomic items there. So at the beginning of this defined behavior tree, I just declare like the actions you can perform here. So basically this is a node in a tree that when it's evaluated is going to end up calling that action on your warrior there. And then the interesting stuff happens down here when you start getting into like these sequences and selectors. You can see that this allows you to kind of build up behavior incrementally. You're building a tree, and you're creating these sequence node and selector nodes instead of having like if and else if and all kinds of conditional logic here. It allows you to kind of say, all right, what do I want to do here? Let's look at a simple example first. Is maybe this fight enemy. So fight enemy is a selector node, meaning it's a logical OR. It's going to say, first of all, I'm going to try to rest in safety, and that kind of breaks down into, okay, am I in a safe place and do I need to rest? If so, then it's going to perform a sequence of actions to get you in a safe place and rest if necessary. And that whole subtree is going to return true or false depending on whether it performed that action. In a selector case, since true means we're done with the selector, if we had to rest, that's going to be your action for that turn. But if it returned false, that means you're either healthy, you didn't need to rest, or you're free to go ahead and attack an enemy or something like that. So you go on to the next case, the sequence. So this selector is either rest in safety, or if you don't need to do that, follow this sequence to attack the enemy, which breaks down recursively into if there's an enemy there, then attack them. So you can see the whole tree concept is very recursive. And so I would like to have a visual of this because it's really hard to explain just by looking at the code, and that's one thing that would be really nice if the DSL was a little bit better in visualizing it too. But you can see the tree is built up from these selector and sequence concepts. So you can follow this branch of the tree, or you can follow this branch of the tree, and it'll do the right thing if you got your conditions set up. Now, one thing we were talking about before was the difficulty in Ruby Warrior. You can't call multiple actions in a turn. Like if this were a live game system, you could probably just call methods on your world and it would have an immediate effect on your world. And you could continue evaluating your tree and move on to the next action and so forth and so on. Ruby Warrior is not set up that way. When you call an action, that's the one and only action you can call, and you have to return up the call stack to let Ruby Warrior take over again. So that presented an interesting challenge here. The way I chose to address it was to use this decorator concept. So decorators are just things that you can attach to nodes in a behavior tree. And they basically wrap around the evaluation of that node and allow you to apply any kind of logic you want there. So like some of the examples they use are a loop decorator. So if you want to perform some action node until some conditions are true, you could set up a decorator that says loop until, and you give it your condition, and it'll keep evaluating that node until the condition becomes true. That's kind of the approach I took with this, except instead of a simple loop, I had to use a Ruby concept of a continuation. So a continuation in Ruby is kind of like a save point. You can create one of these continuation objects, and what it'll do is kind of mark that point in your code, and it'll save your whole state around your program, your call stack, your local variables, and everything. And it gives you a handle to jump right back into that point in code there. And I kind of use that concept to implement this looping here. So you can see I've got a couple of these nodes that are wrapped with continuation decorator. This rest until healthy here. This is kind of like this is a behavior that spans multiple invocations of the play turn. So you want to call rest until you've reached some threshold of health. So you have to call rest, it goes back to Ruby Warrior, and it calls rest again until you're healthy. And I chose to do that using this continuation concept. So basically the idea is I wrap the rest action, which is just an atomic action, it just calls Ruby Warrior.rest, and I wrap it in this continuation thing, and I give it this condition in a block at the end here. So you can see this rested at the very end. That's the condition it's going to evaluate each time it calls this continuation. So once that rested predicate becomes true, the continuation is going to exit basically. So as long as that condition is false, the continuation is going to stay alive, and each time it goes back into the behavior tree, it's going to jump immediately back into that point in the tree and skip evaluation of everything else. So, yeah.
So what basically happens is this thing just walks the decision tree,
Mm-hmm.
and then once it hits this continuation, it just loops there until the condition. So the tree's just locked into that looping state until the condition is true.
Yeah, so that's effectively true. So the way it's written right now, at least, the whole tree is evaluated from the root down to until it finds an action each time play turn is called. However, if one of these continuations is in effect, that kind of takes over the whole evaluation of the tree. Instead of doing the whole root down evaluation, it jumps immediately into that continuation point right where it left off. And I'll show this wrapper. Sorry. So this is my behavior tree implementation. It's not pretty at all at this point, but it did the job for this Ruby Warrior problem anyways. So we have classes that represent each type of node. You got your action nodes, your condition nodes. Branch nodes is kind of a generalization of sequences and selectors. There's a subclass to represent each kind. But the interesting bit really comes in this continuation decorator here. So, like I said, a decorator is anything that wraps around any single node in the tree and alters the behavior of that node. And here, the main method on all these nodes is just called behave. Probably would be more Ruby idiomatic to call it call, but I was following the examples from other languages where they call it behave. So each node implements a behave method that does whatever that node is supposed to do. And in the case of these continuation decorators, it uses Ruby's call CC method, which creates a continuation object. This is your save point. Unfortunately, I had to stuff it into a global variable, which means it's not going to work if you want to have multiple trees in the same system. So it's a quick, easy hack to get things working, but obviously would need to be improved to be able to support multiple trees. But anyway, you create the continuation at that point, and once that continuation is there, you've marked this spot in the tree. And now what it does is it creates the continuation to create your save point, calls block.call, which is the block in this case is that termination condition that I mentioned. So when the warrior is healthy in this case, in our example case, that will return true. So, but as long as that condition is false, it's going to evaluate the node, and it's going to return the continuation back up the tree, so the tree knows, okay, I've got a save point I need to go back into next time I try to evaluate this code. And otherwise, once the block becomes true, that means we're no longer in that continuation case, and we just nil out the continuation so that next time we come in, it'll start evaluation from the top of the tree again. So this is an interesting hack. It allows us to do looping within Ruby Warrior, even though Ruby Warrior kind of wants to control how you do your logic in your player. So it's not the prettiest thing I've ever seen, but it is effective. And yep.
Do you know what the difference between the continuation and a fiber is?
Yes and no.
But I think fibers maybe do similar things.
Yeah, I started doing it with fibers, and I didn't complete the implementation with fibers. I got it working with continuations, but yeah, if you're using fibers, instead of creating this continuation object here, and I guess I don't show where that continuation is actually called. But,
it's right there on line +3. Return behavior tree. Sorry, 3 down.
oh, yeah, so it's returned there. But it's called up here. Yeah, so here we go. So this is the branch node. This is either a sequence or a selector or any of those inner nodes on the tree. This is where the continuation is called. So if it's present, then call it. That's where we get our jump into our save point. If this were fibers, it would be very similar. Instead of using call CC and returning a continuation, you would just say fiber.new, and in that fiber, the only difference is that you have to explicitly yield out of the fiber into your calling context, which it made it a little more complicated in my initial efforts, and this provided the kind of instant save point for me, which I thought was a little simpler, but it does have the negative effect of having to store it in a global variable, or some similar ugly thing.
Where you can refactor later.
Yeah.
Yeah, it doesn't have to be global, right? You could have
Right.
saved it in a class instance variable or something.
Yeah, the only difficulty is that we have kind of like a hierarchy of objects here. So you either have to put it somewhere where all of those objects can share the same reference to it, or you have to kind of propagate it up the call stack. And so the global variable is obviously the easiest way to accomplish everybody seeing it, but there are certainly better ways to do that. And so yeah, I'd like to actually make this behavior tree available on GitHub or as a gem or something, but it's not ready yet. Particularly, it doesn't support multiple trees or concurrency or anything like that, but it does get me through at least part of Ruby Warrior. And I'd also like to kind of improve the syntax of the DSL. Like this, although it's flexible and effective in defining behavior trees, it's not really intuitive when you're looking at it what that tree is actually going to look like. So that the DSL could certainly be improved to make the tree structure more obvious.
Doesn't mean you don't have. Doesn't prevent you from pushing it.
Certainly.
Push it.
How can we fix it if it's not put?
That's right.
How can you criticize it?
Yeah, but yeah, so like I said, I didn't get to a solution with this yet, just mostly because I ran out of time. But I think it's a good foundation to build on, and it provides a nice logical structure. And what I like best about it is it allows you to wrap up bundles of logic into like a single entity, so that you have that hierarchical structure to your logic, and you can avoid a lot of the spaghetti and call in and call out and everything. So
It seems like it gives you another useful layer of complexity on top of the command pattern too.
Yep.
Basically, the command pattern is just a selector, right? The way we were looking at it before.
yeah, exactly. So the command pattern, as we saw it last week, has some equivalent of these actions, right? You have some representation of an action, and I think the way James presented it was just an array of available actions, and it went through in order and tried them all, and whichever one was successful first bailed out the process. So yeah, so it's effectively just a single flat selector node in a behavior tree. Yeah. Yep.
Pretty cool.
I just got one question. Why do you freeze the tree in loop instead of just doing re-entering the tree for each move?
Why do we freeze the tree? You mean like using the continuations?
Yeah. Why do we freeze at a decision point instead of just starting from the top each time?
Well, what freezing allows you to do is allows you to kind of specify this is my current state, state in the sense of like a state machine. We have entered this state based on some condition, but that condition isn't necessarily going to be true the next time you come through. The classic example of this is you want to rest when you get below a certain threshold of health. But you don't necessarily want to stop resting after one time, right? So you want to back up and rest for a little bit, regain some health. And if your criteria for entering the rest state is that I got below 5 in health, say, the next time you come through, you've rested, you bump up to 7. And so you're going to get into a different path in that tree. You're no longer going to enter, oh, I need to rest state. So you'd have to program kind of explicit state transitions if you didn't save your spot in the tree.
I guess there's an assumption that if you're resting, you're not going to have the enemy come up and hit you.
Yeah, so there's some retreat logic in here too. So if you're taking damage, it tries to back up into a safe spot, and that doesn't always work, I found out.
There are archers that can hit
Yeah.
you while you're resting.
Yeah, they can.
That's what I'm thinking, because if you're resting and you keep taking damage, you
Mhm.
need to take a different action.
Right. So
Okay, so
that's what this retreat to safety action is about. So this is another continuation type. It performs the retreat action continuously until you are no longer taking damage. The assumption is that you'll eventually retreat to a safe spot. I don't know if that will always hold true, but at least in the levels I've done it so far, it does hold true.
We
So
haven't seen chasing enemies yet.
yeah.
okay, well, that's what I was wondering, because I'm thinking about this from a much more complete battle system.
Yeah. Yeah.
It's like here I'm thinking some of the enemies I've had to deal with in Guild Wars. It's like they keep coming after you.
Yeah, right.
Yeah, so this is a pretty static behavior tree. People that are using this in the real world, I guess like the new Halos are using this kind of setup, and some of the first-person shooter games are all using behavior trees as like their underlying architecture, but they're all very much more dynamic. You know, it's you're not necessarily doing a top-down evaluation of the whole tree each time, and it's not your state isn't necessarily updating in ticks. You know, it's a constant stream of information. This is very turn-based, and the world changes in a very predictable way. So,
So in there, they're probably trying to manage memory, right?
yeah.
Not have to, yeah.
Yep, very much so.
But the continuation is not an essential part of the behavior tree, right? That was just
Yeah,
how you maintain your state in this implementation.
right. So the behavior tree concept, none of the articles I read on behavior tree even mention continuations, except maybe as behavior tree as an alternative to continuation-based finite state machines. But I thought they actually fit pretty well to allow you to save your place in the tree, so you don't have to reevaluate, and also so that you know kind of what the world was like leading up to this point, and you can stay in this subset of the tree until the world changes according to your criteria. So keep doing this part of the tree here until you're no longer taking damage.
I like how it reads. It's really good. So have you ran this against the basic levels?
Yeah, but I've only gotten up to like level 5 or 6 or something like that. So I was actually
good.
working on it today. And
Yeah. No, that's pretty cool.
Well, it basically only has like one thing, right? It's just fighting or walking.
Have you reached a level that
Yeah.
has an archer?
yes, and
Yeah, I think
that's the last one I passed. This one, this one introduced the captives, and I haven't programmed any captive logic into there yet, but obviously you would need some sort of selector node to check your captive condition, and
yeah.
so
It seems like you got a pretty good DSL that wouldn't be too hard to do that, so
yeah,
it's pretty awesome.
yeah, I think I'd like to, it's kind of there, but I think I want like a builder concept to it, so that like you're building up a tree just like you're building an XML document. You're building a tree. I think that would map really well into this kind of scenario. So yeah, actually,
Then you have 10 problems.
yeah,
Then you would
I actually thought about doing the tree construction in YAML, since you know. That's one interesting approach, and so
I think you'd get really deeply nested. Well, you'd have to just have a way to break that up.
yeah, so that's kind of why I broke. You know, you could build this whole tree top down and have a very tree-like structure, but that would get super hard to read. That's why I kind of broke out some of these things into their own variables, just to give them a name. So this subset of the tree is named retreat to safety. So you have some way of thinking about it instead of like expanding that logic inline into these subtrees there. But yeah.
Yeah, I like that.
So you kind of have that flexibility. You can put your nodes, define them inline, or you can name them with some variable and insert them into the tree wherever you want. And of course, the nodes are always reusable anywhere in the tree. So.
I like it. If I didn't say that before.
Oh, I'm glad. Yeah, I think it's a interesting technique, and I'm gonna try to carry it on to the higher levels and see how well it scales to the greater complexity that comes along.
Yeah, I'm really curious what happens when you get into the intermediate level. Like, I feel like you're constructing something that could deal with some of that complexity pretty well.
Yeah,
Now most of the yaks are shaved, so it should be easy to do.
exactly.
Yeah, famous last words.
Yeah, I don't know how many times I said that along the way, but
It's very cool, man.
yeah.
You should totally push this up on
All right.
GitHub, if nothing else, just for people to be able to read it. I mean, even if you're not done, I think you have a lot
Yeah.
of good stuff here. So
Yeah, there's a lot here.
Yeah, and there's a lot of decorators that could be added to this. There's I created one just called a pry decorator that opens up a pry console. So like you can throw that onto any node, and it'll drop you into a console that you can just inspect what's going on around you.
it'll
And
just be very handy inside of Ruby Warrior while it's running.
Yeah.
You can push it up as a Ruby warrior implementation as opposed to a behavior tree. That way you won't have to feel
Yeah.
bad that it's not.
That's
a
true.
behavior
It's
tree.
It's like,
It's-
okay, I'm stuck. Appeal to the human.
Ruby warrior behavior. Nice.
cool. So that's all I had, unless there were more questions about it or comments.
I kind of want to pair with you now.
Yeah.
Some more tonight. That's awesome.
Yeah, it does kind of change the way you think about the problem a little bit. It gets back into more like the logic programming with Prolog or something like that. You kind of have to think about problems in that way instead of, it's more of a declarative style instead of an imperative style once you start setting up these trees. So. But if you are interested in learning more about this, there are lots of articles and videos on aigamedev.com, I think. But I mean, just Google behavior trees and read anything except the Wikipedia article, which is not about the same topic. So.